need a medium. Radiation does not need a medium to travel through. Radiation does not need a medium to travel through. Yes?
Is it medium?
Medium, like high, medium, low. Okay. And so let's explore what the, ooh, yay, it's working. It's so exciting. Form of radiation, hit from all directions from the source, does not need a medium to travel through. Okay, so let's talk about the word medium for a second, because that's a little weird. Oh, Jesus. So, what'd you say?
The no-no word.
The no-no word, Jesus? Yeah. So, when you hear my voice as I'm speaking, the reason you can hear it is because of the medium that it's traveling through. Although we don't really think about it, this room is filled with air molecules. Okay? If it wasn't, we wouldn't be able to breathe. Now, if this room was absent of air molecules, there was no air molecules, I could scream as loud and as long as I wanted to, and you would not hear me sitting exactly where you are. So the reason that you can hear me is because my voice is causing the air molecules to vibrate and then come into your ear and make that same vibration, which carries a sound. Okay. Yeah?
I have a mini question. I hope that we might learn this about space. Why do astronauts float when they're in the space?
Why do they float?
Yeah.
Because of the absence of gravity. There's no gravity in space. The reason that we're stuck on Earth, okay, we're standing here, is because Earth has mass and therefore it has gravity. Yeah.
And that's called like it's a magnet and stuff.
So you can think of gravity as like a magnet, but the core creates a magnetic field around Earth, but that's not what keeps us put their feet on the ground. Yeah. Exactly, so that's what I'm getting to. So radiation does not need a medium to travel through, which is great, because just like Colson just said, space has no anything. It's a vacuum, it's empty. There is no air, there's no molecules, there's no gas that's present in space. It's just empty, completely empty. So if you screamed in space, no one would hear you. It is, okay, and maybe you've heard that before. Electromagnetic energy travels at the speed of light. Thank you. So the speed of light is the quickest thing that we know of in the entire universe. The fastest traveling thing ever is light. So electromagnetic energy travels at that speed. Okay? And as we'll see later in the period, electromagnetic energy can take many forms. Okay? And you'll see that in a second. So how does it travel through space if space has nothing? So space is a vacuum, which like we said just before, has nothing. No matter, no gas. There's a few planets floating around, a couple stars, some gas and dust. But for the most part, it's really just a bunch of empty space. It's a vacuum. And since electromagnetic radiation is made of exactly like it sounds like, electric and magnetic energy, the wave, which is how radiation travels, carries itself, which is really important. So this electric and magnetic wave carries itself through space, which is wonderful because the sun gives us energy. Oh, thank you. And the sun, if it was not able to give us that energy, we would not feel its heat during the day. It wouldn't warm our planet up at all, and we would likely not exist. So it's really great that radiation has these properties. Okay? So again, it moves as a wave made of a mixture of electric and magnetic energy, and the wave carries itself, which enables it to travel through something with no matter. Okay. Any questions on electromagnetic radiation at all?
Is that like dangerous?
We'll talk about them in a second. Some types are very dangerous, especially to us. So now we're going to talk about waves. And these are some definitions which keep in mind, but I'm not going to ask you ever on a test, what is the definition of this? Okay, that's not the kind of test that I give. So wavelength, frequency, crest, and trough. So just copy those down and then we'll talk about them. and we'll label the different parts of a wave. So wavelength is the distance between two wave crests. Frequency is how many times the wave repeats itself. The crest is the peak of the wave, and the trough is the lowest part of the wave. And the most important definitions on this page are wavelength and frequency. So these two are the most important. 1 and 2. 3 and 4, I kind of just would expect that if I use those words, you may be able to identify them or know which part of the wave I'm talking about. But by far, wavelength and frequency is kind of the basis of what we'll be talking about today. So we're just going to discuss the meaning of that right now. So labeling the parts of a wave. I'm going to draw a wave and try to draw yours as close to mine as you can. Okay, so I'm going to start my wave over here. And I'm just going to make it go across all the way to the edge here. And then we're going to label the parts. Yes.
So let me get this right.
The distance of, it's pretty much just one complete wave is a wavelength. One complete wave. It could be from this starting point to this starting point. Okay, and so you can kind of start to see how many waves are on here. Or you can measure it from crest to crest. And so there's a couple different ways. We'll label 2 different wavelengths. They're both the same though. So from this top to this top is a wavelength. And it's just like the word says, the length of one wave. And you can also measure wavelength from here to here. So this is also wavelength. It doesn't always have to be a crest. You can measure from a middle point to a middle point, a trough to a trough. The wave should have the same wavelength throughout. So now let's talk about frequency. Frequency is how many times the wave repeats itself. So here's one wave to start with. From here to here is one wave. So if you do this with the rest, can anyone tell me how many waves they see of what I just drew? What is the frequency of this wave? How many waves do you see if this is one wave from here all the way to the next spot? Then how many waves do you see? Samantha.
6.
Let's see. 1, 2, 3, 4, 5. So we have 5 total waves. That's our frequency.
I think I drew one extra one on my paper.
Yeah, no, you may have more on your paper. On mine, it's 5. So why don't you, before you write this down, check yours. How many waves did you draw on your paper? Okay, if you have different than mine, that's fine. Just note that so that you understand what frequency means when you're studying. Even if you have like a half of a wave, you can include that as well. Okay, and so that's a wavelength. And in general, wavelength and frequency have an inverse relationship, which means generally the bigger our waves are, the bigger the wavelength, the less frequent they are. Because it would be hard to kind of pack them into a smaller area. And we'll look at that here. So wavelength and frequency are kind of opposites of one another. They have an inverse relationship. If one increases, the other decreases. And so I want you to look at these 2 waves. You have wave 1 here and wave 2 here. Which one has a greater, let's see, which one has a greater wavelength? Which one is a longer wavelength? Even if you don't want to share your answer, think about what I'm asking you. What do you think, Sarah? What'd you say? The top one, yeah, exactly. Wave 1 has a bigger wavelength. If you see, they measured it, in this case, from crest to crest. But this is one wave. This entire length is one wave. Then you have a little extra here and here. So there's probably like 1.5 waves here. So this one has a large wavelength. And before, this is one complete wave from start to finish. This is one wave. And then we have this other one, so maybe that's a half. So we have 1.5 waves here. Now let's look at wave 2. It's more frequent. Which one do you see the most of, Cole? The bottom one has a higher frequency. And the top one, since there's only 1.5 of them, has a lower frequency. It's not as frequent. And frequency has to do with how big the wave is. The bigger the wave is, the less space you have for other waves. You kind of see that? This one's like so stretched out that it takes up more than half of the line just with one of them. Whereas this one, they're so kind of squished together that you can have more of them in a smaller area. Does that make sense? So that's why we say that wavelength and frequency have an inverse relationship. Yeah?
It kind of reminds me of a cyclic or
Yeah, cyclic graph. You're right. This is exactly a cyclic graph. But just making a distinction here, the relationship between wavelength and frequency is inverse. But when we are at the bottom of the page, you should see the same exact thing in your notes on the top of page 2 as you do at the bottom of page 14. Now I'm going to be writing some notes on this. I would write your notes in your reference table, not in the actual note packet, because you'll be able to use this later on tests and quizzes, and it would be more helpful for you to have them in your actual reference table. Oh. Okay, so decreasing wavelength and increasing wavelength. So this is a word we just talked about before. Okay, so if I have an increasing wavelength, what does that tell you about radio waves? Are they a larger wave or a smaller wave? Yes. If I'm increasing the wavelength, larger wave. Good. So over here by radio waves, we're just going to write large wavelength. Sure.
I don't want to mess you up though. Should I just minimize this?
I'll do it.
Yeah, go on. Unless it's like fine. Let me see. Yeah.
Yeah, it's just the internet. I mean, it's raining, so that's what happens. It'll probably pop back on
Oh,
when.
now it says end. Did it just? Oh yeah,
It's fun.
Sorry.
Okay. No worries. So large wavelength, and then over here by decreasing wavelength, we're just going to write small wavelength. Okay, and now let's talk about frequency. So if I have large wavelengths over on this side, think about how frequent they can be. So if I have a really large wavelength, the wave is really stretched out, is that going to have a high frequency, lots of them? Or is it going to low frequency? Exactly. So we're going to write that over here too. Low frequency. And what that would look like would be like this. Really stretched out. And now over here, when I have really tiny wavelengths, my frequency is much higher. And what this would look like is like I took this wave and I just smushed it together. So a much higher frequency where the waves are much closer together. And of the electromagnetic spectrum, as you transition from this to this, your waves would eventually get closer together and closer together and closer together until you had this kind of spacing of your waves, okay, just to give you an idea. So really wide waves, large wavelength, not very frequent because they take up so much room, and then they transition to these really high frequency waves. And so when I say something is high frequency, that can start to tell you something about the kind of energy that that wave produces. High frequency radiation is extremely damaging to humans. And so if you notice the types of radiations on the left-hand side, gamma rays, which we already spoke about, we use for destroying, and death, they're not something you want to come across. You have X-rays, and you also have ultraviolet. Okay, so yeah, question.
Isn't ultraviolet the sun?
Yeah, so the sun produces pretty much all of these, not so much these two, thankfully. The sun can produce ultraviolet. Ultraviolet gives us sunburn. So you don't always know if you're being exposed to ultraviolet until you get home from the beach and go take a shower and then you look like a lobster. That's when you know you've been exposed to ultraviolet. If you don't wear sunblock, you kind of like giving yourself up to that ultraviolet radiation. So ultraviolet's what gives us sunburn, and we don't perceive it right away. We just feel the heat and light from the sun, but we don't know we're getting sunburned until later. That UV is almost undetectable by us. X-rays from the doctor. Has anyone ever gotten an X-ray before? Yeah, same. It's not dangerous if you get an X-ray or 2 X-rays, 3 X-rays a year, but you don't want to go more than that. So when the doctor gives you an X-ray, do they stay in the room with you? They leave. And if you go to the dentist and get an X-ray, what do they put on you to kind of block some of that?
Like this, like leather.
Super heavy, right? It's actually made of lead, which absorbs that radiation, because you don't want the radiation to touch the rest of your body. You only want it to go where it needs to go. You don't want to expose yourself to that, because if you did, you would start to create cells that turn into cancer cells. You kind of deform parts of your body. So X-rays are helpful in small quantities, but if you expose yourself on a daily basis, you would start to develop cancer.
And when they, like this one was saying, when you go to the dentist, what do they do when they press that button? They step outside the room, the button outside the room, because they're being exposed to that on a daily basis.
For sure.
Several times.
So dangerous, yeah. And then when you go, let's say you go to the dentist and you're sitting in the chair and they have that, they stick that picture thing in your mouth that cuts up the roof of your mouth. You know what I'm talking about? That thing's awful. But then they take the X-ray thing and they put it right here, so that the X-ray radiation's only going to the spot it needs to go. It doesn't go to the rest of your body. Okay? Oh, the dentist gives me a little PTSD, honestly. So X-rays, helpful but also harmful, depends. And gamma rays, really, they can damage us. We really don't want to see them. Infrared is another way of saying heat energy. So if you held somebody's hand and they were very warm, that's infrared that you're detecting. Microwaves can cook our food. They're not really damaging to us necessarily, unless you like stuck your head in the microwave and press start. I don't know. Don't do that. That's like a Tide Pod thing, please. I don't need to tell you that you shouldn't do that. And radio waves, we can hear. That kind of makes sense. All right, so let's talk a little bit about it, and then I have some questions for you. So the electromagnetic spectrum is continuous, which means each type of radiation overlaps the other. So you can see overlap here and here, here and here, and X-rays. There's no one set place where, okay, radio waves stop and microwaves begin. That doesn't exist. They kind of blend together. So there are no breaks between where one wave type starts and another ends. Okay, now visible light, because we haven't talked much about visible light. So this visible light column that you see here exists between ultraviolet and infrared. So in this tiny little gap right here is this whole visible light. We've expanded it because visible light's important. It's what humans have evolved to see. So visible light is a band of visible colors we can see. Pretty much the rainbow. Now find the color red once you're finished copying this down. And tell me, is that a longer wavelength or shorter wavelength than the rest of the colors? So find the color red, and remember this whole thing is squeezed in between this gap here. Is the red a longer or shorter wavelength? I'm going to be asking you a bunch of questions like this in a second. Colston. Longer wavelength, exactly. It's over on this side, which is by the longer wavelength side. Which means violet is the shorter wavelength. And most energy given off by the sun is visible light. The sun can give off many different types of these radiations, but mostly it's visible light. This is important. If I took the time to write that in your notes, chances are you need to know that for a test or a quiz. And so I have a bunch of questions for you to try to answer. We'll get through most of them. So take the next 5 minutes and do your best on answering these. We'll go around the room and I'm going to pick popsicle sticks and see who can answer what. Okay, so try to answer some of these questions using page 1 of your notes and the reference table.
This one, do they need to know the order of the visible light in the whole spectrum?
Since it's in the reference table, they will not. While you're doing that, I'm just going to take attendance. Yeah, I know. I always get them confused too. Yep. Okay, giving you about like 1 or 2 more minutes. And then we'll just kind of go around the room and get some answers here, and I'll reveal them up on the board as well. And there's 13 questions and 13 of you, so 13 chances for choice. Yes. And you're having trouble with that last I will help you. Well, I can help you with it now, actually. So if you're stuck on 13, I'm going to give you a clue. The ozone layer helps protect us from getting sunburn. So that is all you should need to be able to get an answer for 13. The ozone layer protects us from getting sunburn. Without the ozone layer, we wouldn't last a minute outside.
Why do we get some?
Because the sun gives off the type of radiation, which is your answer for 13.
Just seems impactful. Some people more than others.
Okay, so I'm going to pick sticks and see how you do. Okay, so question number 1. Oop. Colston, in what type of motion does energy travel? Waves, good, exactly. In a wave, an electromagnetic wave, exactly. Number 2, Ava, what makes one type of energy different from another? There's really 2 answers to this. Exactly. Depending on the wavelength, the length of that wave, or how frequent it is, it changes from a death ray to what we hear as music. So it's really amazing, actually. You just change that property of the wave, and you get a whole different way we can perceive it and the way the wave interacts with the environment around us. Great. Okay, number 3, Cole, which type of energy has the shortest wavelength? Good. Gamma rays all the way on the left-hand side of the page. Those waves are really closest together, so they have the shortest wavelength. Nice. Brody, which type of energy then should have the longest wavelength? So gamma rays have the shortest. What should have the longest? Radio waves, exactly. Very nice. Okay, so make sure you use all the kinds of energy. Camden, which color of visible light has the shortest wavelength? Violet, good, exactly, because that is the type of light that's closest to the left side of the page. And Carolyn, which color of visible light has the longest wavelength then? What'd you say? Red, exactly, good, very nice. So as you go toward the right side of the diagram, what happens, Giancarlo, to the size of the wavelength? Is it getting larger or smaller?
Larger.
Larger, good, very nice. You guys are doing awesome. And Mick, as you go toward the left side of the diagram, what happens to the wavelength? Good, nice. So this one is a difficult one. Let's see. Samantha, you get the hard one, sorry. Can you list me the colors of the visible spectrum from the shortest to the longest? Harmful to the humans. Oh, she's still not back yet. I'll save hers. So Michael, what type of energy is most dangerous to us? Gamma rays, good. The most high frequency would be the most dangerous to us. Sarah, which part of the spectrum can humans detect with our eyes? Visible light. It's visible, so we can see it. We can detect it with our eyes. Exactly. Good. Okay. And number 12, Angelina, infrared energy. How do we detect that as humans? Heat. Exactly. We can feel it with our sense of touch. Good. And so the last one, we can maybe just get a volunteer. So I said, which type of energy is absorbed by the ozone? And then I kind of elaborated on this, and I said, this type of energy is what's responsible for giving us sunburn. So what was that, Ava? Ultraviolet, exactly. So that does it for today. How do you guys feel about electromagnetic spectrum, okay? Yeah? Okay, so let me give you your homework for tonight. This goes on Google. If you have questions for me, now's a good time. Nice job today. So I'm going to come around and give everybody checks for getting correct answers, and I think a class check is in order as well. Okay, so just leave your contracts out where I can see them. Close. Almost full. You guys are on fire.
I need two more. Next, we were, I need two.
Colson, do you need a new one?
This week I really don't want to work no problem, and we need to do it Friday.
Yes.
Winter vacation, well, not winter, Christmas vacation, here's some homework I've been asked about.
Yeah, and I'm doing that shortly. I swear, Miss, you know, they give us Christmas stuff, working the school, taking the speakers.
Homework?